I'm going to talk about Mars today, and I'm going to talk about some of the work that has partly come about as a result of the InSight mission to Mars, but actually some of the work that we've been doing in my group for a while, in fact, using satellite-based observations, mostly of Mars's magnetic field, but also just thinking about interior structure for Mars in general. So this might be a little different style of talk from some of them that you're used to. I'm going to really focus on some of the observational-based things that we've been able to infer, mostly from the perspective of Mars's magnetic field. So just a little bit of introduction to why would we care about studying magnetic fields. Of course, they can be used as a probe of planetary interiors. And so my background is geophysics. And so, broadly, I'm interested in how planets have differentiated, planets and moons have differentiated, and then evolved from there into their current state. And so magnetic fields actually are a unique kind of data set that provides us information on the deep interior, particularly in the case of terrestrial planets, ones with silicate outer shells and metal interiors. They provide us information on the deep interior, the core of the planet, but they also provide information on the near surface rocks, particularly if there is a record of an early global magnetic field in the rocks near the surface. So they tell us not only about that history of the magnetic field, but about the processes that have generated and then affected rocks in the crust of the planet. And then, of course, whether or not a planet has a magnetic field, whether or not it has an atmosphere, fundamentally affects its interaction with the solar wind. And this leads to time-varying magnetic fields driven by current sources in the region around the planet. And those time-varying magnetic fields provide us not only information on these interactions, but they can also be used to probe the planetary interior, in particular, to look at the electrical conductivity of the interior structure. And what you'll see for Mars towards the end of the talk is that this hasn't been possible yet. It's actually been something that I've been involved with, looking at other planets in the inner solar system. But it's something that we hope to be able to do ultimately at Mars. Okay, so for people who don't think about Mars every day, we'll have a little bit of an introduction to Mars, and in terms of geography and just overall interior structure and sort of timing of major events on Mars. And then a little bit of introduction to the magnetic field. And then I'm going to spend a lot of the talk looking at our recent results and work, thinking about the timing of a previous global magnetic field on Mars and how we can actually try to get at that and what the status of that knowledge is. And then more recent work that we've been doing, looking at these time-varying fields and at their sources and the potential for actually doing sort of future interior structure measurements with them. Okay, so just to start out for Mars, this is a global map of the topography of Mars from the Mars Global Surveyor mission. You see this well-known dichotomy between the northern hemisphere, which is smoother and lower in elevation, and the southern hemisphere, which is much rougher and higher in elevation. So this dichotomy has been kind of the subject of many studies for Mars. Its origin is not well understood. There are really two competing, completely different ideas about its origin. Is it internally generated, so related to the interior early convective patterns and crustal production on Mars, or an idea that's really gained traction over the past about a decade, is that perhaps the northern lowlands actually formed as the result of a giant impact. But no matter its origin, it's basically the oldest feature that we see on the surface of Mars. Then in terms of just geographical provinces, there, of course, is the Tharsis region that I outlined here in the dotted line. This is a major volcanic province So for scale, 10 degrees of latitude on Mars is about 600 kilometers. So this is an enormous region. It comprises the major volcanoes, Olympus Mons, which is, of course, the tallest volcano in the solar system at 20 kilometers height. And it alone is large, but the volcanic province is immense. It occupies a huge amount of the planet's surface. There are major impact basins that have been known for a long time on the surface. I've labeled 4 of them here. There's actually been a lot of discussion in the literature about about whether or not there are in fact more than this number, some of them buried in the northern hemisphere, but there are at least 4 of them. These date from, we think, around 4 billion years ago. And then, of course, there's been the much discussed evidence for very different climatic conditions on Mars in its early history, namely through the observation of valley networks that some of which look as though they may have been carved by water. Again, their origins, whether they are all required the presence of water on the surface or whether they could have been carved by subglacial processes, this is a matter of discussion. But again, no matter what, they indicate a very different early climate. So in terms of a major timeline, so this timeline is in billions of years, and most of this action happened in early Mars's history. So from times that predated these major impact basins to somewhere around 3.5 billion years ago. And so a lot of what we look at in terms of talking about Mars, when we talk about things being young, we often still mean 3 billion years or so in age. But the thing to look at here, right, is this major episode of volcanism that probably actually generated much of the volume of Tharsis and continued on until a couple of 100 million years ago, at least. Much of that was very early, pre sort of 4 billion years. The evidence for different climatic conditions extending from maybe 3.9 to 3.54-ish billion years ago. In terms of the magnetic field, it doesn't have a global magnetic field today, but there are magnetized rocks on the surface observed from satellite orbit that indicate that Mars did have a dynamo in the past, and that will be the subject of some of the discussion here. So one of the things that I wanted to mention before we get to that is when we look at from satellite at magnetic fields that are generated by magnetized rocks, if we want to look at that in terms of timing of an ancient dynamo or the history of the crustal rocks, we have to think about how that magnetization might have been acquired or erased. And there are 3 main mechanisms that are important. One is a thermal acquisition. The rocks cool below their Curie temperature and essentially record the magnetic field strength and direction at the location of the rocks at the time they cooled. Rocks can also record a magnetization as the result of shock. The physics of this isn't very well understood, in particular, how that physics manifests for different magnetic minerals. We know it happens, we've observed it in terrestrial rocks, but being able to go from that, even a qualitative argument to quantitative arguments is pretty tricky. And then they can also retain a magnetization or acquire a magnetization by chemical alteration. So you might make rocks at a time when there was no magnetic field, but then perhaps they are altered in the presence of water. Specifically, that can generate things like magnetite in the rocks, which is a very good recorder. And so if that alteration happens at a later time when there was a magnetic field present, then the rocks can actually record the magnetic field at the time of the alteration. And conversely, for all these processes, if any of them happen to rocks that carry a magnetization, but these processes happen at a later time when there's no global field, then you can erase the magnetization. So in terms of time varying fields, just a little bit of an introduction here. Mars sits as an obstacle to the solar wind. It has a thin atmosphere compared with that of the Earth today. And that obstacle essentially generates a shock. The interplanetary magnetic field is draped around the obstacle. There are also electric currents that are generated in Mars's upper atmosphere, in the ionosphere, and the interaction of those currents with the interplanetary magnetic field can generate time-varying fields. And those time-varying fields will have different periods. You can easily imagine from this figure that they would have a diurnal variation, a day-night difference, both from the ionosphere and from this draped interplanetary magnetic field. But there are also periods present that are that result from the fact that the orbit of Mars is inclined to the equator, the magnetic equator of the sun. And so Mars goes from being essentially in the southern magnetic hemisphere to the northern magnetic hemisphere. And so the polarity of the interplanetary magnetic field lines switches, and it switches with a period that's the synodic rotation period at Mars. So on the order of, well, it switches on the order of half of that period every 13 days or so. And then there are additional variations that you might expect to see related to changes in Mars's heliocentric distance, so on the order of a year. Okay, so the kinds of data sets that we have for looking at magnetic fields basically come from orbiters. There are two main spacecraft that have been important at Mars for this: Mars Global Surveyor in the late 90s, early 2000s, and more recently the Maven spacecraft, which is currently still in orbit. Then even more recently, we have, for the first time ever, magnetic field measurements taken on the surface of Mars by the InSight mission. So I'm going to talk a little bit about some of the results from each of these missions. So first we'll look at the Crustal magnetic field. So from Mars Global Surveyor, it was known actually almost right away when Mars Global Surveyor went into orbit around Mars. What was detected were regional scale magnetic fields, clearly not indicative of a present-day global field today, but indicative of magnetized rocks at the surface. And these have been studied in considerable detail. Many different global models for the magnetic field from observations have been made. And I'm showing just one of these in this top map here. It's the radial component of the magnetic field at 200 kilometers altitude above the surface of the planet. And so you can see a few important results from this. They show up in any analysis of Mars Global Surveyor or more recent satellite data. The first is that these magnetic fields are weak or absent over the northern hemisphere and strong over much, but not all, of the southern hemisphere. Over this Tharsis region, there are fields that are present around the edges, but not over the main part of the region. These major impact basins appeared, at least in Mars Global Surveyor data, to have no magnetic fields over them. And there was discussion about whether or not the valley networks actually correlate with some of these stronger anomalies. And so these observations together have been used over the past 20 years to think about the timing of when this magnetization would have been acquired. And the main driver, there's sort of two different hypotheses for the timing of the ancient magnetic field. And both of them are really controlled by this observation of no magnetic fields over these basins. So the two hypotheses are, one, that the dynamo, Mars's dynamo, was actually inactive until after the formation of these basins. So the crust that formed here and that was heated and cooled, shocked, heated and cooled during the basin formation, all of that happened before a dynamo was present, and the dynamo switched on, magnetized rocks after that. So this was this idea for the late dynamo. This is actually a tricky hypothesis because, in fact, there's the ages of most of the surface materials in this region is actually much older than the timing of this dynamo. So in this hypothesis, most of the magnetization has to be acquired by reheating and cooling of rocks beneath the surface. So their magnetic age is decoupled from their surface age. So this is an interesting idea, but was somewhat unsatisfying because it really wasn't very testable at the time. The other idea is that the dynamo switched on much earlier and in fact was done operating by the time of the formation of these major basins. And so that much of the southern hemisphere crust was magnetized, and then you form the basins during a time where there was no global magnetic field. And so you essentially remove the magnetization within them. So there were these two ideas in terms of thinking about Mars's overall evolution. This is an important question because this later dynamo here would have overlapped in time with this time of a very different climatic condition. And of course, whether a dynamo is needed to maintain an atmosphere is something that's a huge debate in the planetary literature. So the main issue here is one I just alluded to, which is this issue of timing, right? The magnetization can be carried by near surface materials. And if it is, then if we have an age based on impact crater densities, proxy for age in planetary science, if we have an age for this near surface unit and the magnetization is carried by that unit, then you can say something about timing. But of course, it can be carried in the subsurface, which could be older, or could have been thermally or chemically regenerated or altered at a later time. And then in that case, it's all hands off in terms of associating magnetization with any kind of timing. And the big issue for us has been that the wavelengths that are resolvable from satellite orbit, of course, are dependent on the satellite altitude, and sort of the rule of thumb is that you can see the shortest wavelengths that you can see are on the order of the satellite altitude. And so for Mars Global Surveyor, this was mostly around 400 kilometers. So you can see things that are 7 or 8 degrees in latitude across, but you can't correlate with more local geological features. Okay, so this has been the basic issue. And one of the things that has been really advantageous for us is the advent of Maven data, because Maven has a very different orbit from Mars Global Surveyor. So Mars Global Surveyor spent most of its time, as I said, at 400 kilometers altitude above the surface. Maven has a much more eccentric orbit. And so a periapsis, its closest approach, comes to within 130 kilometers above the surface. Sometimes, occasionally, it's been as low as 100 kilometers. But of course, it spends most of its time at much larger distances. This has also been very useful because if you think back to the figure of the interaction with the solar wind with the planet, Maven spends part of its time actually in the solar wind. So it moves between these different magnetic field environments. And this was by design. The Maven mission is actually a mission to try to estimate present day rates and mechanisms of atmospheric loss at Mars. And so Maven has been really geared to understanding the atmospheric and plasma environment of Mars with a view to understanding its atmospheric and climate history. For our purposes, it's these really low altitude observations that are hugely important and allow us to basically re-examine the crustal magnetic field, to look at it in higher resolution. And so we've done this globally. I'm going to focus here on a couple of regions that are super important to the story of the timing of the dynamo field. The first is the Northern Hemisphere. We mentioned that in Mars Global Surveyor data, this was mostly absent of magnetic fields. And so the question has always been, is that because the crust is unmagnetized, or is it magnetized but more weakly or at shorter spatial scale lengths? such that it just wasn't observable in Mars Global Surveyor data. And now we can look at that. Then I'm going to focus on a volcanic region here. And it turns out these two regions, the first region actually provides us with some information that I'm going to just touch on, not really talk about in detail, about the earliest timing of the dynamo. And the second region provides us some information on later timing of the dynamo. So the first region here is the Northern Hemisphere, basically. And what I want to motivate mostly with this slide is not so much our result, but actually the idea that these lower altitude observations are really important. So in the bottom left is the topography again. The dashed line is the equator. This black solid line is the proposed outline of the basin that was formed by an impact, if you think the Northern Hemisphere was formed by an impact. And then these other regions, the white lines here, denote major volcanic provinces, Tharsis and Elysium. And then these funky dotted dashed lines indicate two of the basins, Utopia and Isidis. And so if you look in Mars Global Surveyor data, this is just data, and it's plotted at satellite altitude at 400 kilometers. And there's data over almost a decade here, right? And so there's really nice data coverage. What you see is basically these very low to zero amplitude fields in the Northern Hemisphere, and then some stuff around the edges, which is actually about the Southern Hemisphere in this particular projection. And so then if we look at Maven data taken at the same altitude, you basically see the same result. There's not as much Maven data at these low altitudes because of its eccentric orbit, but you see essentially the same result as with Mars Global Surveyor. And now as we walk around clockwise here, what you see are Maven data at now 300 kilometers altitude, then 200, and then under 180. And so what you see really clearly here is even just with this twofold decrease in spacecraft altitude, you see magnetic fields that are increasing in strength with decreasing altitude, indicating they're internal to the planet in origin. And that you also see that in fact you're picking up shorter spatial scale lengths in these magnetic fields. So you can do things like make a global spherical harmonic model for these. We've looked at that with colleagues, but I just want to focus here. What you see with the models is what you see in the observations. They tell this story. The main result here that we talked about in some detail, and I'll just mention it, is you see that in the Northern Hemisphere, most of the Northern Hemisphere at these low altitudes is devoid of magnetic fields. But these are regions that have been affected by later volcanism, Tharsis and Elysium, by impacts, Utopia and Isidis. And in fact, the one region that has not been affected by later volcanism or later impacts actually shows magnetic fields. And so we propose, we had some more discussion of this, but one of the things that we proposed with my former student, Anna Mittelholz, is that these magnetic fields in the Northern Hemisphere do indicate a dynamo that was present. They seem to be uncorrelated with any kind of surface features that are younger in age, and that they may in fact be a relic of the production of this crust at the time of its formation. And so they could actually extend the dynamo back in time to Mars's earliest history when this dichotomy was formed. For a lot of people, the more interesting question is, I think that's really interesting, thinking about when did a dynamo switch on, but for a lot of people, it's the later timing that's really of interest because of this issue of, was there a global magnetic field at the time of a very different climate? And so this second region that we looked at pertains to this particular question. So this is a region near the equator. So this bottom figure is 20 degrees in latitude, so what, 1,200 or so kilometers in north-south extent and about the same in east-west extent. And this feature here is a volcano, and there's a major essentially volcanic flow, pyroclastic flow. So this is thousands or almost 1,000 kilometers in extent. This pyroclastic flow is huge. And this, on the basis of its crater density, is thought to be about 3.7 billion years old. And it's also thought to be sourced from this volcano. And in Mars Global Surveyor data, what you see are magnetic fields over this region. They're non-zero, but they don't really show a very good correlation with the geological feature. And so there was some discussion in the literature, maybe these indicate that this unit is magnetized, but it's pretty unsatisfying in terms of, again, looking at any kind of spatial correlations or really knowing whether it's the surface unit that's magnetized or whether, which is very probable, that at least some of the deeper subsurface is magnetized, because this is subsurface that is northern or southern hemisphere units that are dipping towards the northwest. So either of these was a possible interpretation. We now have Maven data over this region, and we have data at around 100 kilometers altitude. They generally support this overall picture, but I want to focus on some Maven data that actually goes across. These are a few orbit tracks that go across the middle of this region. And what you see are the tracks here, and they're colored by magnetic field strength. If you prefer to look at the radial field component, that's on the right-hand side. The left-hand side is the field strength. And then basically the field strength is plotted kind of in a projection along the track here by these wiggly lines. And what you see is that there is a very strong decrease in the magnetic field strength, almost not to zero, but it goes down to about 20% of its maximum value. And it's right over this crater, where the tracks cross this crater. There's a change in sign of the radial field component. And these observations would be consistent with basically a change in magnetization across this crater. And the crater itself is actually quite small. It's a 35, well, small from the satellite altitude perspective, large if you're on the ground. It's a 35 kilometer across crater, but it's actually modified the ground and the subsurface around it over at least 2 crater radii. So the sort of thermal effect of the crater has extended over about 100 kilometers in diameter here. And so what we looked at were actually models for a uniformly magnetized layer. So we made the hypothesis that maybe this near surface unit is magnetized. And what if you then actually make a hole in it that has the geometry of this crater, the larger modified region around the crater? You essentially make a magnetic hole in this subsurface layer, and you predict the magnetic field profile that you would get from that. And when you do that, you actually see a magnetic field signal that accounts for about 70% of what we see. And so our inference from this is that it is very likely that much of the magnetization in this region, not all of it, but much of it is carried by this near surface layer, because what you're really seeing is the signature locally around this crater of a hole generated by the crater and its slightly larger spatial thermal extent. And so then the question is, well, how thick is this layer? What's its age? Can we then say anything about the dynamo? And there's actually quite a few things that you can infer from this. The important point here is I think this is the first place on Mars where, at a spatial scale that's not thousands of kilometers across, we've actually been able to correlate the magnetic field observations with the surface geology to be able to infer that, in fact, at this location at least, the magnetization is carried in this near surface layer. So this impact crater is about 1 kilometer, 1 to 2 kilometers deep, just over 1 kilometer deep. And in fact, it penetrates much of this younger, on the left-hand side, this is a geological map. And so this boring light gray unit that's labeled as HTU, this is this pyroclastic deposit that's thought to be about 3.7 billion years old. And when you look at the geology and the topography locally, this unit is probably 1 to 2 kilometers thick. So this crater is actually penetrating most of this unit. So that's, those things together give the inference that in fact, this younger unit may be carrying a lot of the magnetization. And so therefore the age of this unit, the surface age of this unit would be relevant to the timing of the dynamo. And so this, I think, is really the first evidence, at least from one place, that there was a dynamo at around 3.7 billion years old. It's actually even nicer than that, because the thickness of the layer that's carrying most of the magnetization, the magnetic field that you observe at satellite altitude is the product of the magnetization and the thickness. It's the vertically integrated magnetization. And so you can actually then start to get a handle on what is the magnetization of the rocks, which is important for understanding carriers in the rocks and the ancient field strength. So the magnetization that's carried, which we can now estimate, is proportional to the product of the susceptibility of the rocks and the field strength in which the magnetization was acquired. And so these things together, combined with the geology of the region, the fact that it's likely that based on the geology of the region, the pyroclastic nature of the flows, that the magnetization is carried by something like magnetite, then using that and using our knowledge of those magnetic minerals, we can actually make some inferences about the field strength, the dynamo field strength at the surface of the planet at the time it was acting. And from this, you actually get the inference that this dynamo field would have had an Earth-like field strength. So these are the sort of the constraints on the younger aspect of the dynamo. And so we can put these two things together, the one that I just touched on here without really any detail, the fact that from these Maven data, we can infer that there was a dynamo at the earliest times in Mars's history. This is actually easy to do from a dynamo evolution problem. Early in the planet's history, the planet is cooling very quickly. It's easy to drive convection in the outer core that could sustain a dynamo field in the core very early in its history. It's very hard to do this from cooling alone after a couple of 100 million years. And so this is a puzzle for the moon. It's always been a puzzle for the Earth. Like, at what point do you need some other source of buoyancy to drive convection in the core? It's a puzzle for Mars, but this is a tie point in the earliest history. Then in the later history, when you definitely need something else going on, we now have a tie point for a dynamo at around 3.7 billion years. And so then really the question is, there's a lot of questions that come out of this. The exciting thing is that this is at the time at which there was a very different climate present on Mars. And so maybe the magnetic field certainly contributed to different kind of shielding of the Martian atmosphere. Exactly how, it's not well understood. The big elephant in the room here is actually the impact basins, right? Because this canonical inference, if you had an early dynamo, has been, well, then it had to have switched off, otherwise the basins would be magnetized. And actually, I think something that's really worth a lot more investigation that we did in a very kind of back of the envelope calculation way in this paper, but it works. One of the arguments that I would raise is that maybe these major impact basins have not necessarily been thermally demagnetized. You just excavated most of the crust that carries most of the magnetic minerals in them. And so they actually have very little to no magnetic signature left because you essentially removed all the magnetic carriers locally. So I think that's something that's really worth some further investigation in the future.
Catherine, sorry to interrupt. We had a couple of questions from Chris Thompson. Chris, do you want to read them, or I can read them out? I think it's sort of a related.
I can see them. I can see them.
Okay, yeah.
Right. So sure, I should have said earlier, you can interrupt me with questions or we can take them all at the end. Either way is fine. So with the dynamo, yes. So the first question is, would the dynamo be delayed if the planet was hottest and most strongly convective early on? Yes. So what matters is the heat flow out of the core mantle boundary, right? So if the mantle of the planet is very hot, then to drive a dynamo, then the core needs to be basically superheated, right? So there's actually quite a bit of discussion in the literature about sort of at what time dynamos might switch on, right? Depending on, and this really depends. It's the very, very earliest history is this comment is probably very true for. I mean, it depends, of course, on the differentiation history, right, and the accretion history. So how much heat is generated as the result of accretion and differentiation in the earliest history. Sort of after you basically differentiate the planet and form a core, then in most cases, it's likely that the mantle is cooling sufficiently rapidly that you can sustain a dynamo. There are exceptions to this. For example, on the moon, you could have had a quite complicated evolution because the moon started out with a lunar magma ocean. So you differentiated the moon to get a core, and then you still had a magma ocean. So you can actually maintain a hot mantle for quite a while. So the details really matter, but in sort of the generic types of models, so these are 1D or even 2D models for thermal evolution, after the first sort of 50 million years, when you've differentiated, you have a core, mantle, maybe a crust, right? Then it would be relatively easy to drive a dynamo. And then how deeply can Mars rocks sustain a permanent magnetization? That's another great question. It depends on where you are, and it depends on that location's thermal history. So if you think about, if you have a very simple model where you one-dimensionally, again, make a planet, make a crust, and then just let it cool over time, and the crust basically cools conductively, then early in the planet's history, so if we think about specific times for Mars, around sort of 4.2 billion years ago, you could definitely maintain a magnetization in the upper 10 to 20 kilometers of the crust, maybe deeper. It depends on the magnetic carrier that's present. So it depends on the Curie temperature of the carrier. Kind of a cool inference for Mars has been, for a long time, it was actually discussed whether or not maybe the magnetization was carried by things like pyrrhotite, so iron sulfides rather than iron oxides. And those are not very good carriers over geological timescales because their Curie temperature is much less. So instead of being 580 degrees C, it's on the order of in the 300s degrees C. In a province like the Tharsis volcanic province, where you've had repeated intrusion of volcanism, you have probably thermally demagnetized the crust over time. So for the present day, it would be possible to maintain a magnetization, but you have to have maintained it through the history, right? So hopefully that answers the question.
Thank you.
And tens of kilometers to the thickness of the crust, depending on where you are, right? Mm-hmm. Okay. So that's the story from satellite observations. It's kind of, it's a story in progress. The thing I would say about Maven data is, unfortunately, we're done with getting these lowest altitudes observations from Maven. Its orbit has been changed so that now it's a little bit less eccentric. And so its apoapsis is lower, but its periapsis is higher. So this is sort of where we are at the moment for lower altitude satellite observations, but I'll come back to this at the end. The other data set that we've had more recently is the data set from the InSight lander. So InSight, as you may or may not know, is a geophysics mission to Mars. Finally, after decades, we got a geophysics mission to look at the interior structure, deep interior structure of the planet. So it carries, its primary instrument is a seismometer, but it also carries a set of environmental sensors to measure everything to which the seismometer is also sensitive besides ground motion. So temperature, pressure, winds, magnetic fields. And so there's a magnetometer on the spacecraft. And this is the first magnetometer to be operating on the surface of the planet. InSight's in a really neat location from the perspective of thinking about crustal magnetic fields, because it's not in the strongest region of strongest magnetic anomalies, the southern hemisphere. It's just north of that. And satellite predictions for the magnetic field strengths at the surface, at the location of InSight, suggested the field would be on the order of maybe 200 to 300 nanotesla. So there would be something that might be measurable there. So in thinking about InSight and observations of the surface magnetic field, either static for thinking about crustal fields or time varying to think about interactions with the solar wind, we have to think a little bit about the magnetometer. It was not a primary science instrument. None of the environmental sensors were. And so it is absolutely non-ideal for doing science. There was no magnetic cleanliness program. It's sitting under the spacecraft deck here, really not where you want a magnetometer. You want it out on a boom. So it measures fields generated by the lander as well as fields generated by Mars. And so all I'll say here is we've done a huge amount of work to try to account for lander fields. And so what I'm going to talk about here are the things that are left over that we are confident relate to fields that are generated by or on Mars. And the data set is basically continuous data at 0.2 or 2 hertz. And sometimes we have some higher frequency observations. Okay, so looking at the crustal field, actually this slide pertains to both crustal fields and time varying fields. So I'll just explain the slide and we'll come back to the time varying part in a little bit. On the x-axis is local time, mean local solar time on Mars. So noon is midday, 0 is midnight. And then going up the y-axis is Sol number. So one day on Mars is just over 25 hours from the start of the mission through 1 Martian year of observations on the surface. So about 2 Earth years. And then these are seasons here. And it's color-coded by the field strengths after accounting for lander-related fields. And you see that during a day, the field varies. We'll come back to that. But the main thing for the purpose of this comment is the scale bar, which indicates that on average, the field is around 2000 nanoteslas at the surface. And so you remember, this is actually substantially larger, almost an order of magnitude larger than the field that we predicted based on satellite observations. And does this make sense? So when talk about this, particularly in the geological community, it's like, well, did you get your predictions wrong? And the answer is no. This is about spatial scales that are observable from altitude. And this is really about the fact that there are clearly contributions to the magnetic field that come from magnetizations that have a scale length that is shorter even than what we can see with Maven data. So these are local regional scale magnetizations that are giving these stronger fields than would be predicted from satellite observations. So this makes complete sense from a geophysics perspective. We can also look a little bit, because we have only one observation, we can't say where beneath the surface this magnetization is carried, but we can actually combine our magnetic field observation with observations of what we think the stratigraphy below the surface is based on geology and what we've been able to infer from seismology. So from seismology now, from a paper actually from earlier this year, we know the crust beneath the InSight landing site is either 20 kilometers thick or 40 kilometers thick. Actually, on the InSight team, there's more agreement around this thicker thickness. This is why the difference. The difference is that there are basically 3 interfaces observed seismically in the data. And there's been discussion as to whether or not the second or the third interface is the base of the crust. But that's a whole side discussion in the literature. But for the purpose of this talk, the crustal thickness at InSight is around 40 kilometers thick. Seismically, there's an interface that's observed around 10 kilometers depth. And above this, the material is quite altered, probably altered by water. It has different attenuation properties, different seismic velocities. And then this 10-kilometer region, we know a little bit about from the geology of the area. We know the top few hundred meters are lava flows, young in age, so less than 1 billion years old. Beneath that, there's a unit, this HNT unit is basically the same age as this unit that I talked about for this pyroclastic flow that we looked at with Maven data. So this HNT unit is around 3.7 billion years. And beneath that is an older unit, 3.9 to 4.1 billion years. And the knowledge of these units is based on material that is excavated at the surface by craters in the vicinity of the impact landing site. So we know something about the layering beneath this, and we can basically then just ask the question, what if? What if the magnetization is carried in a region that extends from the surface downwards, perhaps just from this 3.7 billion year layer downwards, or in the deeper layer. And when you do that, you get constraints on the magnetization of those units that I won't talk about in detail here, but there's really 2 hypotheses, and we wrote about this in a paper last year, and we offered both of these hypotheses because at the time, actually, our paper on the Maven data was basically in review. But my own feeling is that this magnetization is very likely carried, at least in part, by these near surface units. And this would also make sense from the perspective of seeing it at the surface, but not seeing it at spacecraft altitude. So it's consistent with, but it certainly doesn't require this longer lived dynamo idea that we talked about based on Maven data. Okay, I'll say a few things quickly about time varying magnetic fields, because I think this is actually a really cool area for future work. So as I mentioned earlier, at Mars, you might expect to observe at satellite orbit and perhaps on the surface magnetic fields that vary on a daily period, at this 26-day period, maybe seasonally, and then perhaps shorter period time variations that would be to do with short timescale interactions of the solar wind with the planetary environment, either in terms of waves that are generated in the magnetosphere or the ionosphere, or transients from space weather. And so we have looked at these both in satellite observations. In satellite observations, you actually clearly see all of these, but in my group, we looked at particularly at the diurnal variations and the 26-sol variations. And the important take-home point from this is that the diurnal variations, so the figure doesn't show this specifically, but the pattern and amplitude of day-night variations at satellite orbits is actually is consistent with those magnetic fields being the result of zonal winds in the ionosphere. So they're consistent with an ionospheric source. Satellite observations are taken above the ionosphere. We now, for the first time, have observations below the ionosphere on the surface. And there was actually a lot of discussion before InSight about whether or not any of these things would be observed on the surface or whether they would be screened out by the ionosphere. What we see on the surface are clear diurnal variations. They have a peak field for whatever reason. I have no idea why I did this. The maximum field is blue here. And so the peak fields are at around 10 in the morning. And if you look at this carefully, you'll see that this diurnal variation also has perhaps some seasonal modulation in it here. We only have 1 year on Mars, but there's definitely the hint of this. And so one of the things that we looked at was, can we make some predictions for what these fields might be on the surface? So the idea is that in the ionosphere, the electrons pull to the magnetic field lines. The ions are actually collisionally coupled to the atmosphere. So there's charge separation in the ionosphere, and the electric current is mainly carried by the ion moving with the winds on Mars. And so if you start with that idea and some knowledge of the top and bottom of the ionosphere, then you can actually use a circulation model to predict the ion velocities in the ionosphere and the charge densities as a function of local time and season. And so we did this. So you get the current density as a function of local time, season, and altitude. And then you can compute the magnetic field at the surface that would result from that current by assuming you can at least get some different M members, assuming it's a sheet current or a line current. One of the things that we really don't understand well at all on Mars, we don't have good observational constraints, is the geometry of those currents. But you can get some M members, and then you can compute the field strength you'd predict at the surface and compare it with your observation. And so this slide shows that. It shows the observation at the surface in this purple line, and the M member predictions in the dashed lines here. And the red lines are basically the same as the black, except they're global circulation models that also include dust in the ionosphere. And so the take-home point from this is that the field strength that we observe at the surface falls right in the middle of these M member predictions. So I think it is very plausible that this results from ionospheric currents, and that there are hints, although the surface data are messier than this simple model, there are hints, in fact, that those surface fields really are modulated by the large-scale dust storms in the atmosphere of Mars. Okay, we have observations too. I'm not going to talk about these in details, but we are seeing short wavelengths or short period variations. These have periods on the order of hundreds to thousands of seconds. They're beautiful little wave packets that you see in the InSight data. They happen at specific local times, often around midnight, sometimes in the early morning, late evening. We don't see them so much during the daytime, but we also have very noisy observations during the daytime because we have a lot of lander-related activities that interfere with our observations. So we're currently compiling these to try to understand their characteristics and their origins. We have seen one signature of space weather in the magnetic field data at the surface. I won't talk about this in detail, but we published that result just a few months ago. And then more recently, I have an undergrad who's been actually looking at pressure vortices observed in InSight data, some of which may or may not carry dust in them, and looking to see whether there's any magnetic signature of those. In general, the answer is no, and this is actually very consistent with the InSight observation that there seems to be very little dust in the pressure vortices that we see at InSight. In fact, there hasn't been a camera observation of a dust devil at InSight. There are observations of dust devil tracks, but it's very clear that in fact the dust lifting capability at the InSight landing site is actually quite different from the other rover locations. But we see a very small percentage of these pressure vortices do have magnetic field signatures associated with them. They're small signatures, and they're consistent with a very small fraction of these pressure vortices coming close enough to the lander, maybe having enough dust in them to just see something. So that's the kind of dust story in what we have observed. Okay, so the outlook, a few things here that I think are really exciting for the future. Obviously, characterization of these time-varying fields and really understanding their origins is very important. The potential to understand better the Martian ionosphere, I think, is really important for understanding atmospheric processes as well as interaction with the solar wind. These time-varying fields can be used to probe interior electrical conductivity structure. And so that's something that we would like to be able to do in the future. A really key thing for Mars here is that particularly these high frequency variations that I showed you, the hundreds to thousands of seconds, these can probe crustal depths in terms of electrical conductivity, which is very sensitive to water and temperature. And one of the part of the volatile inventory that is not well understood at Mars is how much water is tied up in the crust. So I think this is a really exciting avenue for future research and hopefully for research from future missions. There are lots of landers heading towards Mars. Mars 2020, which is on a unit that has a similar age to this younger unit that we think is magnetized based on Maven data, and the InSight results are consistent with. Mars 2020 doesn't carry a magnetometer. It will ultimately return samples, and so actually looking at those samples to understand whether they're magnetized or not will be really important to magnetic field science. The Tianwen-1, the Chinese lander, is to the west of the InSight landing site. It does carry a magnetometer. It's on the rover. It's switched on for about an hour a day on some of the days when they're operating. And in fact, we right now, in fact, today, are hopefully acquiring some joint observations at the same time with InSight and with Tianwen-1. So this will be really exciting for the future. And then ExoMars is coming up. ExoMars will carry a magnetometer also. So in fact, quite a lot of potential here for landed magnetic field science. And then from a perspective of not orbital, but lower than orbital, there is really now a big push. You can see it's really well motivated, even just by the Maven data and by the InSight data. There's really motivation for getting observations at altitude, but much lower than satellite altitude, to be able to look at not just one place on the surface, but to be able to look at least locally and look at the magnetic fields close to, but not at the surface. And so there are various efforts underway. I'm involved with a couple of them to possibly put magnetometers on helicopters. Ingenuity, that has been successful tech demo from Mars 2020, the helicopter on Mars 2020 is really providing the motivation for this. So to possibly put magnetometers on helicopters in the future, but also drones, long-lived balloons would be really great observational platforms for magnetic field science. So lots of potential for future observations, and I'll leave it there and take questions.
Thank you very much. Do we have any questions from the audience? I have just a sort of a general question. So you have these, you mentioned some global circulation models that you use to learn about the magnetic fields carried by these zonal winds. What are the, so I've heard GCMs mentioned in a couple of contexts. I'm not really familiar with them. What is actually involved in that? Is it like a magnetohydrodynamic simulation, or what are the equations solved, and how does that work?
Yeah, so most of them are not MHD, right? Most of them don't really even include the ionosphere. So we have used, so I would say I've just used it from a user perspective. I'm not an expert on the MGCMs. The code that we have used, or the product that we've used, is from the French group in Paris, the MGCM from LG, I'm forgetting the acronym, anyway, from IPGP in Paris. And they have at least tried to couple some of the atmospheric dynamics to sort of the upper atmosphere, really to try to get the upper atmosphere, the uppermost atmosphere, into these codes. So they're really not MHD codes, they're HD.
Okay, I see.
Yeah, this is the big issue, right, for magnetic field stuff, right? And my understanding is that it's actually getting and coupling the thermosphere properties to the atmosphere below that in these codes that is really tricky. And I'm honestly really not sufficiently familiar with it. I have to go and look it up again, right, to remember what it is that is difficult. I think it's observationally just the types of observations are very different. The observational constraints are really different.
Mhm.
But this seems to be kind of a big sort of stumbling block in these codes. And then the spatial resolution is okay, the vertical resolution is not.
Right.
Very
Yeah.
good, right? So we use this solely to try to get at the ionization profile and the winds.
Mhm.
We didn't use it to try to, and we used those then to just literally like predict the fields, use a biosaval, right? And an approximation about the current density. So it's kind of a quasi-static picture, just using the current densities from it. So, and my goal wasn't to go any further than say we're in the right ballpark even, right? Which is what this shows. I mean, I think going beyond that is really not useful without, codes that are more specific to the local region, actually. And they need to have an M part in them, and then they need to be more specific to the local region that you're looking at, right? Because it's also not clear the extent to which those models are really the ionospheric part. So one of the things that's a problem in those models actually is the winds at ionospheric altitudes.
Okay.
And again, I don't understand the details, but I think the wind estimates at ionospheric altitudes are kind of a guess.
I see.
They have, and I don't know what it is that, I don't know why this is. I mean, presumably it's to do with the fact that, you go from this regime where collisions are important to not being important, right?
Yeah. Okay.
Yeah. So that, so my goal with this was to just say, is this in the right ballpark from an order of magnitude perspective, if you just make really simple approximations? And is there really anything in the time evolution that, looks similar, right?
Mhm. Yeah, that makes sense.
And I think it's promising, but I don't think you would want to do more than that. There's been one study that looked, so a couple of years ago, that basically took an MGCM and then coupled that to right? So coupled that to an MHD model for the ionosphere, right? And did it in sort of a quasi-static snapshot kind of way, right? To try to predict from that the currents at the surface. But again, there's, I mean, all of these things, there's just, the spatial resolution is really an issue in that study, right? Like if you really, what would be used, that study I think would be very useful in terms of if we had a bunch of magnetometers over the surface of Mars, and you could say, yes, broadly here, it looks different from over here, right? Because you've got in the MGCM, the MGCM is global, and they can twiddle knobs to make it maybe higher resolution locally, but is it better truth locally? You don't know, right? And so like that kind of study, I think would be really useful if you could do something with that and say, oh yeah, okay, the field strength here is really different from over here, right? And we see that in the observations, right? To actually look at the study that did that, tried to say, here's what we would see as a function of local time during the day. And I think that that is really not very well resolved. You have to run these models for a while to achieve steady state. And so the timescales are, then the timescales over which you've had to run them are longer than the timescale that you're trying to model, right?
Right.
So
has anyone are there people doing local scale simulations? Like, I mean, in stars, you have lots of boxes that approximate some small patch of the solar structure.
I don't think so yet, because I think the data sets haven't really warranted it, right? Either the sort of detailed knowledge of the atmospheric properties locally, or the magnetic field measurements. There weren't any locally, but I think that this would be a really cool thing to do, right? As we move forward, right? Because just actually understanding, one of the things that's really different at Mars is it's not at all apparent why you would have large spatial scale ionospheric currents, right? At the Earth, they're organized by the global magnetic field, and Mars doesn't have one. So it's really unclear what the spatial scale of the ionospheric currents is. And the other thing that's really cool and challenging at Mars, right, is the dynamo region in the ionosphere. Even if the winds were the same everywhere, the dynamo region is location dependent because it depends on the ambient crustal field, right? The heights at which the electrons and ions are, the ions are coupled and the electrons are not, right? The height at which that happens depends on the ambient field, right? Because the gyration frequency depends on the ambient magnetic field, and the ambient magnetic field depends on where you are, right? At 100, I mean, we know that from Mars Global Surveyor, right? It depends on where you are at 100 to 400 kilometers altitude. And so, and the base of the dynamo region actually moves, when you look at, if you just do some simple calculations for it, the base of the dynamo region can be below or in, or even just above the peak, the altitude of the peak ionization profile. So exactly what part of the ionization profile is really contributing to ionospheric currents, right, can vary with location. There may be places where the ionospheric currents don't matter at all, right? And it depends, and so this depends on it depends somewhat on the collision frequency, right? But it depends, you know, in an ambient way, it depends on the magnetic field strength locally, which varies because the crustal field strength varies by a couple of orders of magnitude, right, at ionospheric heights. And then it also depends on somewhat on season, because the collision frequency depends on season. So it's a really rich area for observations and studies, right?
Yeah, it seems like there's a lot.
Modeling studies, yeah. Mhm.
So we're a bit past time here. I think people have been dropping off. So I'll just thank our speaker again, and I'll stop the recording here. Thank you.
Okay, Alyssa had their hand up, but I can wait.
Oh, sorry, I didn't see that. Alicia, if you'd like to.
Hello, hi, Catherine.
Hi, how are you?
I'm good. How are you?
I'm good. I'm good.
I'm just wondering, is there a sense for what kind of set of observations would be required to resolve the discrepancy between the sort of the two major hypotheses for the dynamo history? Like what it would actually take for observations, and the upcoming missions will potentially have that capability to sort of end up favoring one over the other.
Yeah, right. So the holy grail is samples, right? You know, because a sample, you can measure its age, you can measure whether or not it carries a magnetization that's actually a remnant magnetization, right? So samples have been like really important for lunar science, for lunar magnetic field science, as well as lunar science, right? So ideally samples, right? But given that sample, it's going to be a while before, you know, the measurements have to be done on the Earth, because we can't do in situ dating, and we can't do in situ detailed paleomagnetic characterization. So, so in the meantime, I think that these lower altitude observations, you know, if you think of being, you know, a kilometer above the surface, right, with a helicopter, you know, less even, right, or, you know, tens of kilometers with balloons, right, then you can start to really look at whether or not, so if you think about the insight region, so our result from the insight region, which, you know, we know the magnetization, we can't distinguish just based on insight data. Is the magnetization near the surface or really in the deep subsurface? If you could look with a balloon somewhere like InSight, right, but over a region around the InSight landing site, right, a balloon maybe tens of kilometers, a helicopter maybe a kilometer, right, you know, you could then at least try to look for things that or for structure in the magnetic field that correlates with surface units, right? Like, I think this is really important. In the absence of correlation with surface units, you can just say, well, maybe it is, maybe it isn't, right? And that's sort of the situation that we've been in. With existing data, one of the things we're looking at is there's sort of a couple of things you can do with existing data. One's been done actually just very recently, but it's clear that one also needs additional lower altitude data for this. There are techniques. The big thing here is, what is the depth of magnetization? Where is the source layer, right? And you can try to get at depths of magnetization, but you can look at essentially how the spectrum falls off, the magnetic field or the magnetization spectrum falls off with wavelengths. And that, for some different assumptions about the statistical properties of the magnetization, you know, it's correlated on length scales of X, or it's uncorrelated, blah, blah. You can then put constraints on the depth of the source layer. And people have attempted this a long time ago with Mars Global Survey data. It wasn't very satisfactory. But more recently, a paper just out this summer looks at a global model for the magnetic field from Maven data, and attempts to get the depths of magnetization. And their inference is that in the Northern Hemisphere, the magnetization is carried close to the surface in the upper crust. In the Southern Hemisphere, it's on average carried more deeply. They have really huge uncertainties, right? So their uncertainties go from above the surface to the base of the crust, right? So So it's true that on average, and my suspicion is that that result is close to correct, right? Based on what we've seen empirically, which is there is in the Southern Hemisphere, other than the fact it's the Southern Hemisphere that carries most of the magnetization. In the Southern Hemisphere, there's really no correlation of relatively stronger or weaker anomalies with geology within the Southern Hemisphere, right? Like whether a magnetic anomaly is sometimes it's stronger, sometimes it's weaker, and there's nothing obvious in either the geology or our best estimates for crustal structure from gravity and topography. And that to me suggests that it's not in the Southern Hemisphere. A lot of the magnetization certainly isn't in the top few kilometers, right, of the crust. So I suspect that that's close to correct, but we could do with much better constraints on it, which would come from these lower altitude observations as well. And then we looked to see if we could find anywhere else with a convenient little crater. And we haven't yet. It's not surprising, right? You need a unit that's that age, and then you need a crater that is sort of relatively fresh and young, so that you're not like dealing with something that's older, degraded. What was the timing of the crater relative to the materials around it? You really want to know that you recently came along and punched a hole in this, substrate. So there aren't very many areas. There's very small tracts of areas where there are surface units of that age where we had the lowest altitude observations, and then you need this, this really nice setup. So it seems like that was a kind of an unusual type of situation, right? But ideally, that's what you want to look for with lower altitude observations, is exactly that kind of thing, right? Yeah.
Great, thank you.
Mm-hmm.
Do we have any other questions before I stop the recording here?
With a few hardy souls hanging on. Thanks to everyone for coming and staying for the discussion.
Well, thank you so much.